Hello YouTube, this is my first video in my module in which we're going to look at a special class of discrete probability distribution in which we have not many different possible things that could occur and some likelihoods that they actually happen, but specifically two. We refer to these experiments as binomial experiments, okay? And a lot of different experiments that we run in terms of like a probability sense, we can look at them as being able to be reduced to two possible outcomes. And we often refer to these things as successes and failures, but I mean, in terms of experiments that we might consider to be, say, binomial experiments, this would be like flipping a coin. You know, you flip a coin, you either land on heads or you land on tails. Or if a child's being born, it's either a boy or it's a girl. We could even look at medical research. You know, when we classify a treatment, we could look at that as either being a success or a failure. Okay, but a lot of experiments that we run, we can, if there are not two possible outcomes, we could at least reduce it to two possible outcomes just by looking at this idea that it could either be a success or a failure. Okay, so experiments that can be reduced to two possible outcomes, such as success and failure, at least what we'll call success and failure, we refer to as binomial type of distributions, and they are so unique that we come up with some shorthand with them, and we work with them quite a bit of the time. So we're going to start by defining what we mean by a binomial experiment. You know, could something be a binomial experiment or not? We say a binomial experiment is the probability experiment that satisfies four specific requirements. The first one being this: it says each trial can have only two outcomes, or outcomes that can at least be reduced to two outcomes. We say these outcomes can be considered either a success or a failure. So again, you know, the examples we gave are flipping a coin, a child being a boy or a girl, or maybe treatment in a medical sense being a success or a failure. We could consider those binomial experiments because, well, each trial of that experiment could be falling into one of two categories. The other stipulations of these, we say there must be a fixed or finite number of trials. So when we look at flipping a coin, we're not saying you're flipping this coin for eternity. We might say that I flipped this coin precisely 500 times. The point here, though, is this. You're only going to run a finite number of trials. We can count the number of times you repeat this experiment. Okay. The last two stipulations are these. We say the outcomes of each trial must be independent of one another. So for example, we've talked about independent probabilities before. We say flipping a coin and say spinning a spinner. The fact that I flipped my coin did not affect the probability that I would spin something there. But in this case, we say flipping a coin. You know, what if I flipped a coin 10 times? Each flip does not affect the probability of the next flip. So we say each probability is independent of the other probability. And that kind of ties in with this last one here. It says the probability of success must remain the same for each trial. So in the experiment of, say, flipping a coin, it's either heads or tails. When I flip the coin the first time, probability of getting a heads is 50%, but when I flip the coin the second time, since it was independent of the first, we say it's still 50%. But that probability of, say, a success must remain the same for each trial of our experiment. But if we can satisfy each of these four stipulations, we could classify an experiment as being seen as a binomial type of situation. It's either one or it's the other. Okay, so we want to get used to these words here. We say in binomial experiments, we are typically classified as either successes or failures. So we'll often do this. We say what constitutes a success, what constitutes a failure. But again, as an example, we say the correct answer to a multiple choice item. You know, let's keep in mind here, we say like maybe I'm taking a multiple choice test and the answers are A, B, C, and D. People like to say, well, this isn't a binomial type of situation, and the reason why is because there are four answers, and that's not one or the other. But what we can do is we could classify it this way. One of these answers happens to be a success. Maybe A is the correct answer here, so we say success is A, and then we say like failure would be all the other answers here. Okay, so just because there are three wrong answers and one right answer doesn't mean this is not binomial. It's binomial because we can classify one of the answers as being success, and it has a probability of occurring, in this case 1 out of 4. And then the other probability is being a failure. Okay, so like everything else, which would be the other 3 out of 4. Okay, so before we dig into this and show the formula for a binomial experiment, let's go ahead and take a look at some notation here. We say the notation that's typically used for binomial experiments are shown below. So we say PS and PF, just to be clear on these, we say PS represents the probability that we get a success, and PF is the probability that we get a failure. Okay, so the interesting thing about it is this. We say the probability that I actually get a success, we actually call this lowercase letter p. So you'll notice here we say lowercase p, this is the numerical probability of actually getting a success. So we say probability of a success, or p of s, this represents theoretically the probability of getting a success, but we say it actually comes out to be this number right here. So for instance, in this experiment that we listed over here as being binomial, we say the probability of success would be 0.25, or a 1 in 4 chance of getting success. And likewise, we say, well, then p would be 0.25 here. We say likewise, the probability of getting a failure. This would be our lowercase q is what we're going to call it. So q is the numerical probability of a failure. That's what it actually comes out to equal, this number. So we say 3 out of 4 in this case, and that would be the same thing as 0.75. Okay, and so one thing before we kind of deviate and go to this n and x down here, we say, probability of success or failure, if it's one or another in an experiment, you'll notice that it was a 25% success, theoretically rate here, then we'd say, well, then everything else would be failure. So it would be the other 75%. So we could say the probability of success plus the probability of failure, we say, speaking here, just perfectly analytically, we'd say this should always add up to 100% of our stuff. Okay. So what are n and x? Let's be clear on this. N, usually we use that to represent the number of data in the data set. In this case, we're going to say the number of trials is this lowercase n. So lowercase n represents how many trials of this experiment we are running. So for instance, if this was a 10-point or a 10-question multiple choice test, all A through D, we would say the number of trials is 10 because there are 10 different times we're going to guess at the question. And then x is going to represent the number of successes that we have in those trials. Okay, so a few things I want to say about this. X is always between 0 and n. Okay, and including that. So we could have 0 successes. We could say how likely it is I get none of the questions right. Or we could say x could actually equal n, the number of trials. We said there maybe hypothetically there are 10 problems on my test. We could say I want 10 successes. But it's always between them. It can never have more successes than I did trials in the first place. And last but not least, we say the probability of x successes, which is what we care about here, is some number between 0 and 1. Okay, so all of this shorthand aside, let's go ahead and take a look at what we have here. We have a binomial probability distribution formula. And here's what it is. It says in a binomial experiment, something that could be reduced to either one or the other, we say the probability of exactly x successes in n trials is given by this formula right here. And you'll notice I've written it 2 different ways, but we're going to pay attention to this first way more than anything. We say it is this expression here, n factorial over n minus x factorial, times lowercase p to the x and lowercase q to the n minus x. That's a lot to remember. The other way I write this is this. I want to just point out that this first expression up front here is the same thing as n choose x. So keeping in mind, n is the number of trials, and in that number of trials, x represents the number of successes. Essentially, what we're getting here then is this. We say we have the number of total trials factorial over n minus x. Now, keep in mind, if x represents the number of successes, we can say, all right, well, n total trials, x is the number of successes, then n minus x would be all this stuff out here. If we took the whole space and subtracted off the x, subtracted it out, we'd be left with this, n minus x. So when we say n minus x, this really represents the number of failures, which would be everything else in the basement, and then x represents the number of successes. Okay, so we're going to pick this formula apart a little bit. I'll rewrite it over here on the side. But then we say, okay, so keep in mind, what were p and q again? P was the probability that we get a success to the x power, where x represented the number of successes we wanted. So we have the probability of success to the number of successes power. And then q represented the probability of failure. And this is to the n minus x, where we said n minus x represents the number of failures, if this is the number of successes here. So we say the probability of failure to the power of the number of failures we have. So to rewrite this out a little bit longer here, we say the probability of getting exactly x successes, if we have n total trials, is this. We have the number of, I'll use s for successes, number of successes factorial over this, number of failures factorial times number of successes factorial. And this is being times this. We say p of success to the power of number of successes, and then probability of failures to the power of number of failures. Okay, and so you do a few of these experiments, man, you get used to this after a while, but it's easy to kind of piece this formula together. So we're going to look at an example, okay, a thought experiment in which we're flipping coins, very, very binomial. And some good habits that you're going to have as you work through these. We're going to do it both, the long way, writing everything out, and we're also going to use the formula to do this and say, well, which one is probably the most convenient. Okay, so example 1 here, let's consider this. It says, consider the following thought experiment. A coin is flipped 3 times. Okay, so this would be the number of trials we do. We flip it once, flip it twice, flip it thrice. We say, find the probability that we get exactly 2 heads with 3 trials. So the most important thing for us when we start is this: we're going to have to say what constitutes a success, okay, and what constitutes a failure. So since the question I'm trying to answer here is this: how likely it is that I get 2 heads if I flip it 3 trials, we're going to say success is get a heads. So failure, we want to write this down at the beginning of every experiment. We say failure then is everything else. We say get a tails in this case. So these things being classified the way they are, I say, well, let's start by doing this a long way and sketch out the sample space. When I flip a coin 3 times, how can we do this? Well, we say, well, we could get a heads, and a heads. Likewise, we get a tails, and a tails. We go 2 heads and a tails. We say 2 tails and a heads, 2 tails and a heads. How about heads, tails, heads, tails, heads, tails, and then heads, tails, 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 heads, heads. So there are 8 possible ways to do this. The question was this: how likely is it we get probability of 2 heads? So we're going to write down the probability we want to find, and we say, well, out of the 8 possible ways to do this, which we've listed here, these 8 possible ways, we see that how many of them give us 2 heads? Well, we say this one gave us 2 heads, this one gives us 2 heads, and this one gives us 2 heads. So we have a 3 in 8 chance, or a 0.375 probability of this occurring, or a 37.5% chance of this actually occurring. Okay, so that's writing it out and doing it the long way. What if we actually use the formula here? Okay, so the formula, a few things I want to say. First of all, we have to still define what do we consider to be a success and what do we consider to be a failure. And you'll always get this by reading the last sentence here. Since we care about, getting heads, we'll call getting head success. We could we could just as likely call a success as being a tails, and then just kind of change the way we interpret this. But that being said, for the formula, we're going to need to know 4 things here. We need to know n, we need to know x, we need to know lowercase p, and we need to know lowercase q. We'll go through these one at a time. So in this experiment, we say, well, how many trials were there? That's n. We say, well, we flipped the coin 3 times. So we say 3 times. We say, all right, how many successes did we want? Well, if a success means we get a heads, we say, well, the probability we want to find is probability of getting 2 heads. We say, all right, 2 heads is the number of successes we want here. Now, P represents the probability of a success. So we have to ask ourselves, well, what is the probability that I get a heads when I flip a coin? And of course, that answer there is 1/2, as a half. Okay, so we say, well, what's the probability of failure? Well, my favorite thing about probability of failure is just everything else here. So we could say it's 1 minus the probability of success. Or we could say, it's just the other half, the other 50%. But now that I know these 4 things, let's write out the probability we want to find. Starting with this, we say probability of x, where x was the number of successes. The thing we're trying to find here is this probability of 2, or 2 successes, or, in this case, 2 heads. That being said, let's go ahead and write out what we know about this formula. So our first expression here is this messy one. We say, well, how many total trials are we doing? We say 3 trials. We say, well, n minus x factorial times x factorial. I'm actually going to start with this. I'm going to switch it around here. I'm going to change my x factorial and n minus x factorial when I write it. But basically, we say, well, how many successes do we want? We want 2 successes. Okay, so that means, well, how many failures do we want? Well, if we had 3 trials and 2 successes, then this is the other one here. We want 1 failure. And then as far as the rest of this formula goes, we're just going to fill in the blanks here with what we need. And what we need are these things. We say, well, we've got P, which is the probability of success, which is a half, to the probability, or to the power of number of successes. So we said the number of successes here is 2. We'll just go ahead and plant that 2 up here. We say, well, what's the likelihood we get a failure? Well, likelihood we get a failure, tails in this case is 1 and 2. We say, well, how many failures did we want? 1. So basically what I can tell you is this: if you can come up with this expression in front, then you're gravy, because basically what we get is this: we have P, we have Q, and then we'll just transplant these numbers up here to be our exponents, okay? So we need to simplify this expression. So this is the not so fun part. We say, well, this would be 3 times 2 factorial on top over 2 factorial 1 factorial, which, by the way, 1 factorial is just 1, so we can get rid of that. And then we say, all right, well, this is a half to the second power times a half to the first power. And simplifying this even further, we say, well, the 2's factorial cancel out, and we're left with this 3 times 1/2 to the second power times a half to the first power. And furthermore, when you raise a fraction to a power, you raise both the top and the bottom of the fraction to that power. So in other words, we get this. Whoops. We get 3 times 1/2 squared, which is 1 squared over 2 squared, so we get a fourth. And then 1/2 to the 1, well, that's just a half. And so multiplying all these straight across, you see that we get 3 times 1 on top is 3, and then 1 times 4 times 2 on bottom. So the formula here, the formula, we got the same thing we did when we just read out the sample space. Okay, so what I want to use the formula the majority of the time, as a matter of fact, the formula is what we want to move ourselves toward. Okay, and the reason why is because it's just not desirable to write out the sample space. Say we had flipped this coin 4, 5, 6, 7, 10, 100 times, and we say, well, you know, if I flip the coin 100 times, how likely is it that I get 70 heads or 70 successes? You could see how this formula would be really tedious to use. So we're going to use this formula, but we're going to start moving towards a set of tables that we can use to determine these. But that, in essence, is what we consider a binomial experiment. And of course, this is the formula that we'll use to evaluate binomial experiments. Cheers.